P on this axis, vapor down here, liquid up here. Now I want you to imagine for a second that you start off at you've got, actually let's start off right here, liquid. You got some liquid under high pressure, and it's at such a high pressure that there's no gas phase, right? And we slowly, and it's got some particular mole fraction, placing it directly above what the mole fraction is of the total solution, Z. We start to bring the pressure down on this guy. And we're going to intersect this curve. At that pressure, the mole fraction of the liquid is given by the intersection of this curve with that guy. The mole fraction of the vapor corresponds to this value over here. So we drop the pressure down, we allow the vapor and the liquid to come into equilibrium. At the pressure at which this mole fraction here is whatever the mole fraction we chose, the mole fraction of the vapor is this guy back over here. This is called a tie line. We draw a horizontal line from this curve over to this curve. That horizontal line indicates that the pressure is constant. Right? The system is built at the same pressure. This curve gives the mole fraction in the liquid. This curve gives the mole fraction in the vapor. Which component, or which component is the most present in the vapor? The one with the higher boiling point, or the higher vapor pressure, or the lower vapor pressure?
Lower vapor pressure.
So this axis down here plots the mole fraction of some component. This is the pressure of that component in the pure, right? Because when the mole fraction of that component is 1, our pressure is this pressure right here. If we move the mole fraction back to 0, the pressure is the pressure of whatever this component is. We can still call it P component 2. B component A and B. Which of these components is more volatile?
Okay.
If it's more volatile, it's going to have a higher or lower vapor pressure? Higher.
Oh.
Yeah, volatile things. Volatile means that the stuff goes in the gas phase really readily, right? And so your component B here, when it's in the pure form, has a higher vapor pressure than component A, indicating that component B is more volatile in component A, or is more volatile than component A. If you look at the mole fractions here, the vapor above this solution moves back to this line, which indicates that the vapor has a lower mole fraction of component A than did the liquid, which inversely means that the vapor had a higher mole fraction of component B than did the liquid. And this is one of the results of Raoult's law, is that the vapor always ends up being enriched in the more volatile component, which kind of makes sense. We said that all the forces were identical, but just in general, it's not absolutely true that the more volatile component still has a chance of escaping into the vapor more readily than the less volatile. Again, if we switched and communicated this graph in terms of the mole fraction of component B, the thing would be inversed, and the relationship would be inversed but still, you would see that when you drop that pressure down, you end up with a vapor phase. Once you bring the vapor phase into existence, it's always enriched in the more volatile component. Okay? So we just did a bunch of math to argue for that pressure versus mole fraction graph to explain where the different curves came from and why they have the shape that they have. There's an analogous curve. So the pressure versus composition curve was generated while holding temperature constant. We picked one value of temperature, and we said at this value of temperature, how do the mole fractions vary with their mole fractions of the vapor phase and liquid phase, for that matter, vary with the composition. If we instead hold the pressure constant at one value and use up that degree of freedom, we can plot a analogous graph where we have the boiling point temperature versus the composition. So the last graph, we had curves that related to the pressure, the vapor pressure versus the composition, and the et cetera. And now we're looking at a temperature versus composition graph. The top line of the temperature versus composition graph is not linear like it was in the other one. Both of the curves in the temperature versus composition diagram have a little arc to them. Without seeing the math, we can't really explain that, but that's just observed. Line is quite reliable. You'll notice that because we're dealing with pressure or temperature now instead of pressure, that the positions of the liquid region and the vapor region are inversed with respect to one another. If we go high in temperature, we end up favoring the vapor phase. If we go low in temperature, we end up favoring the liquid phase. And so liquid and vapor are reversed in their positions. We can use this graph in an analogous way to the way that we use this one. I'd say just start, for the sake of learning how to use it, pick an arbitrary mole fraction where the total composition of the system has some particular value of z, and start at the point and tell yourself that you're going to increase the temperature. When you're down here, where the temperature is lower than the boiling point temperature, you're entirely in the liquid phase, right? We start to bring the temperature up, we move up, 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 up. At the point that we hit that curve, we cross the boundary between being pure liquid, and we reach equilibrium where liquid and gas or liquid vapor are present together in that system. The intersection of this guy with this curve will show what the mole fraction is that you expect to have in the liquid. And if you draw a tie line from, a horizontal tie line from this curve to this curve, the intersection of this curve will tell you what the composition is going to be in the vapor, right? So, draw this guy. This is the same one for the benzene and the dichloride, I think. You pick a spot, you come up here, you overshoot this guy a little bit, you can draw a tie line back to here. The intersection here shows the composition of the liquid. Draw a tie line to this side. And this guy shows the composition of the vapor. Which component is the vapor enriched in? The more volatile or the less volatile component. This guy has a lower temperature at which it reaches equilibrium between the liquid and the vapor, right? This guy, whatever component is over here when x is equal to 0, so component B. Component B reaches equilibrium between vapor and liquid at a lower temperature, therefore it's more volatile. And so you'll see that the vapor moves backwards along this thing, indicating that the mole fraction of component A decreases, the mole fraction of component B is increasing. Therefore, again, we look at this graph and we can tell that the vapor is going to be enriched in the more volatile component, right? And so, go ahead.
Maybe I'm not understanding this graph correctly, but you have a line that tells you the fraction that's going to be liquid.
Yeah, well, the x-axis runs from 0 to 1.
Right.
When it's 0, you've got all of one component, and when it's 1, you've got all of the other components,
Yes.
right? And so, if this is component A on the x-axis, then when we go all the way over here to ZA is equal to 1, then we have pure A, right?
Yes.
If we go all the way over here, where ZA is equal to 0, we have pure B,
Oh,
right?
Okay. Okay. Yeah.
And so the vapor pressure, or sorry, the temperature at which vapor-liquid equilibrium happens for component B is lower than it is for component A. Component A, you gotta have a higher temperature to bring yourself up to equilibrium between the liquid and the vapor. And so this guy is more volatile. And you'll see, based on these tie lines, once you come up here, the stuff that's remaining in the liquid line moves over here, and this portion of the line gives the composition of the liquid. This portion of the line over here gives the composition of the vapor. The vapor has decreased in its concentration of component A, therefore it's increased in its composition, or in its concentration of component B. So it's becoming enriched in the more volatile liquid, or the more volatile component. And so you can look at either one of these graphs, a pressure versus composition or a temperature versus composition, and you can draw the conclusion that for these ideal systems, the vapor is enriched in the more volatile component. So this is how the whole fractional distillation thing is done. You stick a flame under something, you start gassing off the stuff, and the distillate that you collect is enriched in your more volatile component, and you subsequently distill it over and over and over again, and eventually you can get almost complete separation where the vapor becomes the volatile substance, and if you keep collecting and distilling the stuff that's left over in your flask, eventually it becomes the pure other substance, right? And so you can achieve a separation by distillation between two components that behave ideally, right? Most volatile component is going to show up in the vapor. The less volatile component is going to show up in the liquid remaining, and separation is achieved. That doesn't happen with all systems. And we're going to look real quickly at a couple of situations where that doesn't happen.
So, but all that is dependent on the mole fraction, right? I mean, say that you have a very volatile alcohol, and then you put like, I don't know, more molecules of that alcohol, then it will delay the vaporization.
Can you please repeat that question in the form of an answer?
Well, I was just thinking, if you have more, if the mole fraction is bigger, even if you have a more volatile component, it will still be in the liquid phase.
It's the mole fraction of which one
Say
is?
for instance, if a B, I guess they just switch places. Got it.
I still don't understand the question, but as long as you understand the answer, that's all that matters to me.
Got it.
Okay. All right. So this is the graph that you use for fractional distillation. I'll just walk you through it real quick here. So you take something that has a particular average composition Z, you heat it up, and the stuff remaining moves towards the right, starting to become pure. The stuff that's in the vapor has this particular mole fraction, right? You condense it, and now you've got a liquid with that same mole fraction. You heat that liquid up, it turns into it reaches its boiling point. It's got a lower boiling point than the stuff before because it's enriched in more volatile stuff. It kicks out a liquid that is enriched in the less volatile component and a gas that's enriched in the more volatile component. You collect that gas, recondense it into a liquid, and now you're boiling this stuff here. You draw another tie line. The next time you heat this stuff up and distill it, you've moved it almost completely towards pure, and so the arrows show you the progression of the vapor as it becomes pure, right? And you could draw analogous arrows for this stuff and say, okay, well, this guy moves over here, I heat it up again, vapor goes that way, the liquid goes back that way, and eventually the liquid goes all the way pure, right? So that's important to pay attention to because now that we've defined the rule, we're going to break it.
You could just use a really big column
Yeah.
and save yourself a lot of stuff.
Yeah, that would probably be the best idea.
Or if they have like a really close boiling point on both two different components.
Then it's gonna be a long day to distill that stuff. Okay, so just I'll say this while I'm on this page. So there's two ways that you can think of a system as deviating from ideally. We said ideally the interactions are all equal in magnitude and nature, but in the unideal scenario, those forces are not equal, and they can be one of two different situations. In one situation, the solvent to solute interactions are stronger, so than the interactions between two solute molecules or two solvent molecules. So the forces that are binding these guys together, individual A molecules together and individual B molecules together, are weaker than the forces that would bond to an A and a B molecule together. And so A and B molecules, in this case, interact with stronger forces. They interact more strongly than the separate solvent or solute molecules. The other way to break ideality is when the solvent and solute interactions are weaker than the ideal interactions. And so these two, the A molecules, bind together more strongly than an A and a B molecule do. And this leads to two different kinds of phenomena in distillation steps. And here is phenomenon number one. So, this guy's fairly easy to follow, I think. We're looking at the surface of a system, right? This is the surface of the liquid. It's in contact with the volume above it, and so vapor can, leave if it wants to. And we've got some solute dissolved in some solvent. And we're going to start distilling. In the case where we've broken the ideal relationship, broken it such that the A-B interactions are stronger than AA or BB interactions. This unit here, where you have a solute molecule surrounded by solvent molecules, will have tighter binding, tighter interactions than the other unit circled here, where you have no solute molecules, you just have solvent molecules. The interactions here are weaker than the interactions here. So which species are going to go into the gas phase most readily? These guys. So units like this that are weakly bound are going to be popping off of the liquid phase and driving off into the gas phase. And in the meantime, units like this that are more tightly bound stay behind in the liquid phase. Right? What that creates is a situation where your vapor ends up being enriched in whatever component was in excess. Ooh. I don't know what the hell I was thinking when I wrote those words. Those are not true. Ignore those words. This stuff up here, you'll see that the concentration moves towards a concentration where there's enough A and B molecules to interact and to create maximal forces. Once the liquid reaches this concentration, it reaches a point where it boils at constant composition. It's the units that end up popping off in the gas phase. Once you've reached the maximal ratio of A molecules to B molecules in one of these maximum boiling azeotropes, though there's nothing that gets preferentially kicked out into the gas phase first, right? You can imagine all of these guys are bound with equal forces. And so distillation kicks out units of the same exact composition once you get to this point. And so you don't get a separation, you don't get one component moving preferentially into the gas phase while the other component lags behind. You get a situation where you boil a constant composition. And so basically, if you have a maximum boiling azeotrope, you can with repeated steps move your vapor towards becoming pure, but your liquid itself kind of moves towards whatever composition is the composition of the maximum boiling azeotrope. So you look at this guy here, and here, say this right, whatever mole fraction this is our maximum boiling mole fraction. This guy has more component A than it needs to be maximum. And so you take a sample of this particular mole fraction right here and you heat it up. The vapor is going to have an even higher concentration of that guy that was in excess. And so the vapor is being pushed towards pure, and the liquid moves backwards in composition until eventually it gets to that point of the maximum boiling azeotrope. You can map that behavior out on the graph. Does that make sense? I think that the pictures are nice. Do I need to put any more words behind them, or is that clear? It's all good. So you could start this, and I encourage you, for the sake of training your mind to work with these graphs, start this at either side of this and say, okay, if I've got this composition XA that's greater than the maximum boiling azeotrope composition, how does that affect what shows up in the vapor and what shows up in the liquid? And you can see the vapor is enriched in whatever component is in excess. Do the same thing over here and just prove to yourself that when you start off with less of component A than you need, that component B gets kicked off into the vapor, and so the ratio of A to B increases, bringing you eventually to the maximum boiling azeotrope.
So this would be like boiling acetone water.
Yeah. Yep. Acetone water, maximum boiling azeotrope. And now for the other one. I'll give you a nickel if you can tell me which systems behave this one and the way the next one is. So the other way to break ideality is to have kind of the inverse situation where interactions between the solute and the solvent are weaker than interactions between two solute molecules or two solvent molecules. In that case, we got the inverse relationship where units where a solvent and a solute molecule are interacting together are more weakly bound, and so they go off into the vapor more quickly. And units where you have simply solvent or whatever component is in excess, those units are more tightly bound. And so you get this phenomena that the vapor moves towards a composition of a minimum boiling azeotrope, but the liquid that remains behind moves towards becoming pure. So, starting right here, let's say that we start out with some initial mole fraction. We begin to raise the temperature. We get to the point of equilibrium. We raise the temperature just a little bit more. The vapor moves backwards in concentration. The liquid moves forward in concentration. So the liquid increases its concentration of whatever that component was that was in excess, and the vapor moves backwards in concentration, trying to get towards that minimum boiling azeotrope, right? Similarly, if you go over here, you heat that guy up, you'll notice that you kick off the component that was in excess over here to favor movement forward towards that minimum boiling azeotrope. And so for those guys, you can make the liquid pure, but the vapor is eventually going to reach a composition at which it boils a constant composition and doesn't become pure, right? You can recondense the vapor and it's still gonna boil at the same composition. So who does that? Who has a minimal boiling azeotrope?
It's gonna be like Spinzelda. Maybe it's even like
Ethanol and water.
Oh.
Yeah, those guys have a minimum boiling azeotrope. That's why they say that you can't create pure ethanol by distilling an ethanol water mixture, because eventually your vapor gets to some minimum boiling azeotrope and it boils at constant composition. So they teach you guys that. And some of the Gen Chem labs work with distillation of ethanol mixtures. But yeah, you can. It's something like your minimum boiling azeotrope has something like an 80% composition of ethanol. And you can't get it any cleaner than that. Well, that's because of this effect. All right. So we only got like 10 minutes left or 12 minutes left. I'm done talking. You guys might have already seen this one, but to show you a problem that I assigned for an exam last time through.
Are we not going to use them?
What's that?
Are we not going to use them?
Does that answer your question? You know, my life is crazy, and I plan on writing your exam when I get home and posting it on Eiler and sending it out by email. So I'll ask you guys to print your own copy and submit it on a printed type or whatever, print a piece of paper. But you'll get it yourselves. I got too much on my plate, get everything done by the deadline. That's why I'm so easy with you guys about homework. Shit, I don't do anything on time.
Give us 4 points for all of them.
What's that?
Give us 4 points for all of them.
That's pretty much what's going to happen. If you guys turn in all of your assignments and it looks like you did a reasonable job, we're going to get full credit for those.
Wait, I thought you told us not to turn them in.
Well, you have to turn them in eventually.
Oh, okay.
Don't turn them in right now. Keep a hold of them for now, but eventually turn them in. Okay, so here are two problems. Both of these are temperature versus composition diagrams. Don't get lulled into a false sense of security because just because I didn't use a pressure versus composition diagram last time through doesn't mean I won't do that this time. But this is just practice in playing with temp composition diagrams. Question A, which degree of freedom is constant everywhere on the graph? When we got a temperature versus composition diagram, we're holding pressure constant. So we've gotten rid of that one degree of freedom. We only have 2 degrees of freedom left, depending on whether or not we have a 2-phase system or a 1-phase system, right? So is the mole fraction, or is the component whose mole fraction is tracked on the x-axis more or less volatile than the other component? Does it boil at a higher or lower temperature? The component that's tracked on the x-axis is when we're at the far end where the mole fraction is 1, then it's that pure component. And so you can see here that when it's pure component A, whatever it is, we gotta boil at a lower temperature, therefore it must be more volatile, right? And so this guy back here, this composition is not tracked, it's the less volatile system. How many degrees of freedom are present along the equilibrium curves?